Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Hanim Akila binti Suhaimi. I will be presenting the elucidation of carbon dioxide generated via biodegradation of bioplastic derived from local banana peel. The purpose of this study was to measure the amount of carbon dioxide released as bioplastics made from banana peels degrade over time. We specifically examined how the different stages of banana ripeness influence the biodegradation process. Why banana peels? They hold significant potential as a sustainable source for bioplastic production. Not only are banana peels widely available, but they are also break down quickly in soil, making them promising material for reducing plastic waste. To assess biodegradability, we use aerobic digestion, where the carbohydrates in the banana peels break down in the presence of oxygen. This process generates carbon dioxide. The more carbon dioxide produced, the more biodegradable of the material. Our study not only promotes a sustainable and environmentally friendly approach to plastic production, but also offers valuable insights into improving resource efficiency. Lastly, we paid close attention to how environmental factors like soil temperature, pH, and moisture content impact the amount of carbon dioxide released during the biodegradation test. In this study, we used several important methods to characterize the biodegradation process of banana peel-derived bioplastics. We employed FTIR spectroscopy to identify the functional groups present in the bioplastic material. This technique allowed us to gain a deeper understanding of the chemical composition of the bioplastic and track the changes that occur during biodegradation. Another key method was monitoring the weight loss of the bioplastic samples buried in soil. By observing how much weight the bioplastic loses over time, we can determine its biodegradation rate. This is a crucial step in understanding the overall breakdown process. Finally, tracking the weight changes of the bioplastic samples at various stages provides a quantitative analysis of the biodegradability. This is vital for measuring the amount of carbon dioxide released throughout the degradation process. By keeping a close eye on the weight changes, we can accurately map out how quickly and efficiently the bioplastic decomposes. Let's move on to the sensory evaluation of the banana peel powder, which vary depending on the ripeness stage. Unripe is a dark brown color, odorless and lumpy. Ripe has a brownish yellow, sweet-smelling and dry. The ripe powder also had a sweet smell. It is proven in research by Nat Shihani in 2020 showed that the sweet smell is due to the presence of esters. Sharper smells are produced when the end ingredient's volatile components are intimately linked to its smell. Volatile molecules called esters are generated during ripening stage processes. Acetate esters are the most common type of esters, making about 50% to 80% of all esters. Overripe powder is a brown, slightly sweet and slightly dry. Similarly, the sensory evaluation of the bioplastic film shows unripe has a slightly full and sticky. Ripe has a sweet smell. For texture analysis, it was brittle and sticky. Brittleness is a sign of fragility and fragility, probably as a result of compositional alterations. Overripe has a rancid, dry and brittle. From the FTIR analysis, we identified several functional groups. For instance, the broad peak at 3,298.5 per centimeter was due to hydroxy groups. Low vibrations in the CH stretching absorption band of the symmetric hydrocarbons CH, CH2 and CH3 at 2,941.5 per centimeter, 2,938.5 per centimeter and 2,919 per centimeter for the unripe, ripe and overripe films respectively. 2,155.5 per centimeter and 2,155 per centimeter for unripe and overripe film are shown for P triple bond C. The higher water absorption by hydrophilic starch and saccharides was linked to HOH stretching and H stretching absorption produced by the primary amine. CO stretching vibrations were identified as the cause of the band at 1,024, 1,032.5 per centimeters and 1,039 per centimeters. Water solubility varied with the ripeness of the bioplastic film. The unripe film had the lowest solubility at 48.9%, while the ripe film had the highest at 74.35%. Low solubility films might serve as shields to improve the product's integrity and water resistance. The overripe film showed 55.79% solubility. The rough surface of the unripe films created a barrier to water penetration, increasing their water resistance. Next, the soil burial test reveals some interesting findings. Wet soil significantly accelerated biodegradation by promoting bacterial growth. For instance, bioplastic films degraded much faster in wet soil than in the dry soil. The moisture content and microbial activity greatly influence the rate of breakdown. The faster biodegradation occurs when the soil is at 80% of its capacities. Now, let's move on to the soil burial test, specifically focusing on the effect of soil pH on the biodegradation of the bioplastics. Our test showed that in neutral pH soil, the weight loss of the bioplastic increased steadily over time. This indicates that the biodegradation process is progressing smoothly under these conditions. As the bioplastic breaks down, the loss of material is a clear sign of microbial activity and decomposition. In terms of specific results, we found that the weight loss in neutral pH soil was 18.36% for unripe bioplastic, 22.71% for ripe bioplastic, and 23.38% for overripe bioplastics. The lower weight loss for unripe bioplastics is worth noting. This is because unripe films contain less sugar compared to the ripe and overripe films. Since sugars serve as an easier food source for soil microbes, the lower sugar content in unripe bioplastics made them harder to break down. As a result, the biodegradation process is slower for unripe films. The difficulty in breakdown means that microbes in the soil take longer to degrade unripe bioplastics, while the higher sugar content in ripe and overripe films accelerates the process, leading to a faster rate of biodegradation. Now, let's look at the impact of the temperature on the biodegradation of bioplastics. Temperature is a crucial environmental factor that significantly affects how quickly bioplastic break down in soil. In general, higher temperatures accelerate the biodegradation process. In our study, we found that biodegradation occurs most efficiently at 35 degrees Celsius. At this temperature, the biodegradability rates for the different stages for banana peel bioplastics were 29.89% for unripe, 29.91% for ripe, and 32.62% for overripe. These results clearly show that all the bioplastic samples, regardless of ripeness, degrade more quickly when exposed to warmer conditions, with the overripe films showing the highest rate of weight loss. In contrast, when the bioplastic was subjected to a lower temperature of 9 degrees Celsius, the weight loss was notably lower, indicating slower biodegradation. The rates were 17.97% for unripe, 17.70% for ripe, and 23.73% for overripe films. Moving on to the aerobic biodegradation measurements, we observed some interesting trends regarding the degradation of the bioplastic films made from banana peel starch. Initially, the biodegradation of the bioplastic films followed an decreasing trend. This means that the rate of biodegradation grows in the early weeks but began to slow down in the later stages. For the ripe and overripe films, we notice a significant increase in degradation rates by the third week. These films, which have higher sugar content, broke down faster due to easier availability of nutrients for microbial activity. On the other hand, the unripe films degraded at a much slower rate. It wasn't until the fourth week that we saw a noticeable increase in the breakdown of these films. The lower sugar content in unripe films likely contributed to this lower rate of degradation, as microbes had a harder time accessing the nutrients. One factor contributing to the reduction in biodegradation rates over time is the development of a biomass layer on the surface of a samples. This layer forms as microbial activity progresses, and it effectively prevents enzymes from reaching the bioplastic surface. Lastly, the delayed biodegradation phases can be linked to a delay in carbon dioxide emissions. After the third week, carbon dioxide production slowed down, further indicating that the biodegradation process was tapering off due to the build-up of the biomass layer. To conclude, our study on banana peel-derived bioplastics yielded several key findings. Firstly, sensory evaluation showed that the films had acceptable qualities in terms of color, smell, and texture, making them a promising candidate for bioplastic applications. Next, the water solubility test revealed that the films exhibit intermediate solubility, largely influenced by the roughness of the film surface. The ATR-FTIR analysis confirmed the presence of biopolymer functional groups within the bioplastic material, validating that the bioplastics are indeed biodegradable. The soil burial test demonstrated the significant impact of environmental factors such as temperature, pH, and soil moisture on biodegradation rates. We found that wet soil and high temperatures notably accelerated the weight loss the bioplastic samples. Lastly, the aerobic biodegradation measurements indicated that carbon dioxide release was higher in the ripe and overripe films, confirming that these films degrade faster due to the higher sugar content, which promotes microbial activity. Together, these findings provide valuable insights into the behavior of bioplastic derived from banana peels and their potential as an environmentally friendly alternative to conventional plastics. That's all for me. Thank you.